Welcome to Thermodynamics.
Hi, my name is Malvadi Sardilia, a second-year college taking up Bachelor of Secondary Education major in Sciences and currently studying at Negros Oriental State University, Bayawan City. In today's video, we would like to explore the different heat engines that operates using the principles of thermodynamics. But before anything else, let's answer this question. What is heat engine? Heat engines is a device that converts heat into mechanical energy.
At this moment, let's proceed to the examples of different heat engines that operates using the principles of thermodynamics. It includes the internal combustion engine, steam engine, and external engine. So let's take a look first for the steam engine. So the figure on the screen will be the example of steam engine.
To understand how it works, let's watch this.
Under 4 minutes. Here we have a steam locomotive. It has two double-acting engines, one on either side. The rest is pretty much along for the ride. There's a boiler that generates steam for the engines, and a tender that carries the fuel and water the boiler needs. The double-acting engine was in use for nearly 150 years and is based on a very simple and elegant concept. When you strip everything down to the basics, all you need to do is move a piston back and forth in a chamber. That's it. To do this, you create a channel connecting each side of the chamber to a supply of steam. Then you supply high-pressure steam first to one side of the chamber, then the other, forcing the piston to move from one end to the other. A sliding valve controls which side of the piston is connected to the high-pressure steam and connects the other side to the exhaust. As long as there's a supply of pressurized steam at the inlet, the piston will continue to move back and forth. For most machinery, a rotating shaft is more useful than an oscillating piston, so the piston is connected to a crank, and the crank rotates. Each time the piston stops and changes direction, there's a dead zone where the engine produces no power. To overcome this, a flywheel is attached to the shaft. The flywheel's momentum carries the piston past the dead centers so that steam can once again enter the chamber and move the piston through the rest of its power stroke. Finally, a connecting rod links the rotating shaft to the sliding valve, keeping it perfectly synchronized with the piston. These are the essential components of a double-acting engine. Steam was used because it's pretty easy to make. As long as you have a supply of clean water and a source of heat, you can generate steam in a pressurized tank called a boiler. The boiler is connected to the engine with pipes, valves, and other equipment. This arrangement powered trains, ships, and all sorts of machinery late into the 20th century. As it turns out, the double-acting engine can also run on compressed air. If you have some power tools, you can build one of these engines out of wood from plans available online. If you'd rather build from a kit, we've developed an inexpensive working engine that you can build with little more than glue and sandpaper. It can be connected to an air compressor, or you can run it on a vacuum cleaner.
So based on the video, it proves that the steam engine is to convert heat energy into another energy, which is the mechanical energy. The heat energy available due to combustion of coal is used to transform water in a superheated steam. The engine utilizes it to produce mechanical motion. Also, we have internal combustion engine. So what is this? So the internal combustion engine is a heat engine where the combustion of a fuel occurs with an oxidizer in a combustion chamber that is an integral part of a combustion of fuel in the internal combustion engines. It occurs inside the cylinder of the engine as the boilers of a steam engine. The engine occupies less space and is suited for small purposes. Therefore, the thermal efficiency and speed of internal combustion engine is higher than that of a steam engine. Also, we have external combustion engine. To understand how the external combustion engine works, let's watch this video.
Now see about external combustion engine. External combustion engine is a heat engine where a working fluid, contained internally, is heated by combustion in an external source, through the engine wall or a heat exchanger. The fluid then, by expanding and acting on the mechanism of the engine, produces motion and usable work. The fluid is then cooled, compressed and reused or dumped. In these types of engine, the combustion is primarily used as a heat source, and the engine can work equally well with other types of heat source. Combustion refers to burning fuel with an oxidizer, to supply the heat. Engines of similar configuration and operation may use a supply of heat from other sources such as nuclear, solar, geothermal or exothermic reactions not involving combustion. They are not then strictly classed as external combustion engines, but as external thermal engines. External combustion engine burns fuel externally, or outside the engine. The burning fuel releases thermal energy, which is used to heat water and change it to steam. The pressure of the steam moves a piston back and forth inside a cylinder. The kinetic energy of the moving piston can be used to turn a vehicle's wheels, a turbine, or other mechanical device.
Based on the video, external combustion engine is a heat engine where an external working fluid is heated by combustion of an external source through the engine wall or a heat exchanger. The fluid then, by expanding and acting on the mechanism of an engine, produces motion and usable work. The fluid is then cold, compressed, and reused in a closed cycle. Unlike the steam engine's use of water in both its liquid and gaseous phases as the working fluid, the Stirling engine is enclosed, affects air or a helium. To differentiate between the internal and external combustion engine, let's take a look at this picture. To have a deep understanding between the two, in the first column is the internal combustion engine and the other column is the external combustion engine. In the first column, the combustion of fuel takes place inside a cylinder. Temperature and pressure is high. Working fluid may be petrol, diesel, various types of gases. Required less space. Capital cost is relatively low. Starting of this engine is easy and quick. Thermal efficiency is high. Power developed per unit of those engine is high. And then fuel cost is relatively high. And then the second column, which is the external combustion engine. Combustion of fuel takes place outside the cylinder. Temperature and pressure is lower. Working fluid is steam. Required large space. Capital cost is relatively higher. Starting of this engine is time. Thermal efficiency is low. Power developed per unit of those engine is low. Fuel cost is relatively low.